Okay, so let's move to the second part of today's class. For the second part, we will talk about B autonomous navigation. Okay, so for robot navigation B, for autonomous navigation. Right, so I will skip this. Just for any newcomer, please off your microphone and also your webcam all the time unless you are do so, right? Unless you are told to do so. Okay, so we already done for mobile robots and also audiometry and localization, so you know. So the next part is we are going to discuss about autonomous navigation, and we have two parts. The first one, robot motion planning, which is give you some idea. We are not going to discuss very detailed about the algorithm or the calculation or model of the path planning, but let you have some idea how robot actually plan for the motion. Okay, then how to use this into to achieve the autonomous navigation, which means the robot can move from point A to point B autonomously without collide into any of the obstacle, and also in the meantime, it also try to maintain obstacle avoidance all the time, which means during autonomous navigation, the robot also can avoid unknown or new or dynamic obstacle. For example, like someone actually passed by, which is previously not in the map, it will still try to avoid. Okay, so that is what we call the autonomous navigation. Right. So the first thing that I would like to share with you is this for autonomous motion generation. So one classic example that we always use for path planning is this what we call the A-star algorithm. So you can search on the internet, like A-star algorithm is like you can find a lot of resources, but basically in a simple form is, okay, this one, path with shortest cost. Okay, so why it is used cost here but not the shortest path, for example, or shortest distance, we don't do that. It's because cost can be anything, depends on your priority. So if let's say your priority is distance, then the shortest distance. But if your priority is time, then shortest time. If your priority is, for example, like the travel cost, for example, like the fees per distance or whatever, then it is the cost and so on. So cost can be anything. It depends on your priority. And in normal case, of course, it's the time or the distance, right? But time and distance is not always true all the time, because like certain distance might be harder to travel than other distance. For example, like you have a more challenging surface, or like you got like a bumpy area and so on. So it is not always true all the time. So that's why we define a shortest cost. So A-star algorithm is used for a simple reason to find the path with shortest cost. Okay, so this is the equation. So if you want to know more, okay, you can go to the internet and find. Right. Then the concept for path planning, okay, so this might be just one classic example. It got a lot of algorithm, like we got many algorithms for this kind of path planning. So I just introduced one, and this is not all of the algorithm. Okay, so this concept can be just one of the example. So for example, we have an environment like this. So you start from a green box, you want to go to the red box or location, okay? And then we have an obstacle in between, which is the blue box. So blue boxes. So these are the obstacle, and then we need to find a path from the starting point to the goal point. Okay, very simple. I mean, like if you look at it, you know, like okay, it will be something like this, or it will be something like this, right? But how you want to make this process automated, which means no matter how your map look like, we have a standard algorithm that can apply in all the time, and I can always find the shortest cost. So we need an algorithm. Okay, so before we start with the algorithm, the first thing we do is we discretize the environment. Discretize means we try to break them down into small unit. So over here is like we break down into small boxes, and each boxes we consider is the smallest unit. For example, like per step. Okay, so the robot will move either here or here, consider one step, and so on. All right. Okay, but of course these can be further smaller and smaller. It depends on how accurate or how resolution you want and so on. But of course, the smaller it goes, your computation will become higher. Okay, right. So the algorithm, or the concept, how to find the path planning is what we call the search problem. So it is a search problem. So for example, like you try to imagine, like if you start from the first point, you want to go to the second point, your possibility of the second point can be either one of these boxes, right? One of these 8 boxes. If you stand on the middle, then you are not moving. So it will be either one of this. So you got one starting point and you got 8 possibility. And then for each of these possibility, it got another set of 8 possibility and so on. But of course, like up to this point, then you got less possibility. Like you got maybe this one, you either move here or move here, you got 2 possibility. If you move here or here, maybe this one also, then which means every point that you go, it will have further more possibility and further more possibility, and until the end, you will have something like a tree, right? Okay, so that is the starting point from where we try to tackle the what we call the search problem. Okay, so let's look at the next slide. So in computer science, we have this kind of search problem widely discussed. Okay, so we call it like the state space and search problem. So try to imagine just now, like we start from one step, and then the following step can be either this stage or this stage, right? So which means just now we got 8, right? But this one only got 2, and then for this one another 2, and this one go to another 3, and so on, right? So you try to imagine this. And how to do this? Okay, so this one is we use one classic example, which is what we call the Tower of Hanoi. Okay, so the Tower of Hanoi actually tell us or give us a very good representative of this state space and search problem. So we can see like this. So what is Tower of Hanoi? So maybe I can show you one example, then you straight away you can understand. So this is one example that I searched on the net, which is the Tower of Hanoi. So all you need to do is like you got this 3 ring. Okay, it can be 4 or 5 or 6, but the simplest one is 3 ring. So all you need to do is like you need to move this ring 1 per time, and you cannot stack bigger ring on smaller ring. You can only stack smaller ring on bigger ring. Okay, so for example, like if now I move like this, I cannot move like this. Okay, I can only move like this, and this one can put on top of this. Okay, so your movement can only go like stack the smaller one on the top. Okay, but your objective is to find the smallest steps in order for you to transfer all this ring to the other side. Okay, you only have 3 pillars, so you either like move all these 3 to this on the right hand side, or from the right hand side to the left hand side. Okay, so just move to this, and you have 1 extra pillar in the between for you to do the transition. So every time when you move one, it's considered one state. Okay, and then you move another one is another state. So for example, like from the first state, for example here, so the second one, you have 2 possibility, either here or here. So from the first point, you have 2 possible, okay, and so on. So if you look at this, this is how you solve. Okay, this automatically will show you how to solve. So this is the first step, second step, third step, fourth step, fifth, sixth, seventh step. Okay, so for these 3, you need to at least have 7 moves in order to complete the task. But of course, you can like reset this, put it to 4, 5, 6, and then you can see there's actually an algorithm to do this. Okay, but eventually this can be solved mathematically. Okay, but I just want to show you the concept on how to do this. So over here we have the stage tree, and then we have the node, and all these things we have this. Okay, but what I want to show you is like by using this concept, we try to solve this, which means every time you go and then you go and then you go. But this algorithm got one more, one more rules that you want to achieve, which is you want the shortest cost. So for example, like you have this 8, you want to determine what is the next step that you're supposed to go. Okay, you always measure this the distance from here to the endpoint, and compared to this one to the endpoint, and see which one have the less cost. And you can see like there are value over here. Okay, so this value indicate the cost for each of the possibility. Okay, so for this A-star algorithm, it used this like every time it got like multiple choice, then it will calculate each of them with respect to the distance to the goal point and see which one is the less. So of course, if you compare this and this will have a longer distance to the goal. So that's why it will choose this one. And then from here, because this one cannot move, this one will be further, this one will be further. So this is the closest to the goal. So it will choose this one and so on. And it repeat this until it reach the goal. So this is the fundamental concept of this A star and how we think about how we use the search problem for the path planning. But of course, like I just explained this in 10 minutes, it's not easy for you to understand, but I hope you can get some idea and you can look further on all those things that I just show you. Okay, then you will understand more on this. Okay, but of course, like we have a very limited time here for me to explain this thing, so it's not possible to explain the whole A-star algorithm, but I just want you to have the concept that how we actually think about this path planning. Okay, so now let's assume like you understand what I have just said. So now you understand that how we actually break this thing into all these boxes and then how we actually find a path eventually by using this A-star algorithm from this point to this point. Okay, so this is the path. Okay, for example, like the shortest one, but of course, like we have another one which is equivalent. This path also the shortest one. So you might find like these two are identical solution for this. Okay, right. So by using this, I'll suggest you try to understand also what is this Tower Hanoi, state space and search problem, and then you'll find a lot of resources for this in order to understand all those things. Okay, right. So now let's say we already have this idea on path planning. So how we want to put this in ROS? Basically, you don't need to do anything because we are going to use another tools, just like the G mapping, straight away directly can do the calculation in ROS. So over here, like just now I explained, we use the adaptive Monte Carlo localization package in order to do the localization. Okay, but this is just for localization. Okay, what is the connection between localization and path planning? Okay, so localization is like, so once you have this path planning, for example, you have this path, you already have this path, how you want to move the robot according to this path from this point to this point. So this is where the localization come in. First, the robot need to understand where the robot located with respect to the map in the real world. Okay, so just now, as I explained in the first half of the class, we use the AMCL to estimate the current position based on the sensor, right? The laser sensor, right? So that is how you do the estimation for the first one, right? Then you are going to move, right? So once you move, you have the odometry, okay? And then you combine with your gyro sensor, you have the odom combine, right? So you move here, you have the odom combine, and this odom combine are going to combine with your next sensor, which is your laser scan, and these two data will be fed into your AMCL, and AMCL will show you the next position the robot's supposed to be. Okay, but of course, every time this process will keep on repeating because like it is repeating to scan the real world and compare with your estimation from your odometry. Okay, so this process is continuously synchronize each other. So which means like they're comparing to each other to make sure like every step is correct. Okay, so that is how like the robot will move one step and then you will do the localization and move another step and do the localization. And this is what happened in the robot later on in the autonomous navigation. Okay, then another scenario that come in. What if, let's say like the robot move here and suddenly someone actually move across here? So if you have a dynamics obstacle, so this is a static obstacle. But if you have a dynamic obstacle? So for example, at this point, when the robot try to scan around for navigation, for localization, something actually passed by, and the scan actually capture that particular moving object. Then temporarily, it will say this path is not accessible. Then what the robot will do is like, okay, it will redo the path planning. It will redo means, okay, so it will color this to become blue. Then it will start to do the calculation from the start again to find another path in order to reach this. Then it will continue this process again to move step by step. So that's why with this algorithm, the robot able to localize, move one step, localize. If got dynamics obstacle, then it will replan the path landing, and then it's try to move. And this will continue until the robot reach the goal. And that is what happened in the autonomous navigation. Okay, so I hope my explanation is clear enough for you. Okay, right. So in order to achieve this, okay, so maybe like you also have enough of the theory part. So let's move to the practical part. You can refer to this autonomous navigation of a known map with Turtlebot. Okay, so this will show you some of the steps, but again, I will invite David to show the steps. So all you need to do is, again, the same thing. What you need to do is like you need to bring up the gazebo, which is, okay, over here I show you the Turtlebot example, but David can show you the Jupyter robot example. Okay, but they are very much the same. Okay, so you can bring this up, so you have the gazebo simulator with your environment and robot. Then you are going to do, like this time you're not going to do G mapping, but instead you are going to launch AMCL. Okay, so in the Turtlebot gazebo or Jupyter gazebo package, you launch the AMCL demo. So just now is the G mapping demo, now is the AMCL demo. And this time you need to specify one more thing, which is your map. Because just now you don't have a map. Just now the purpose is to build the map. And then after that you save your map. So now when you want to use the AMCL for navigation, you need to specify, you need to tell the robot where is your map file. So over here, your launch, you need to put in one argument, which is a map file is equals to, okay, you need to point to your map, where you save the map or which map you need to use. You need to specify over here. Then the rest are almost the same, like you launch the RVs in order for you to see the map, and also like you can do some interaction, and you can send a goal. Okay, so there are three ways to do the navigation. One is you can use the GUI to send a goal so that the robot can move. Okay. Another one is you can actually get the point. Okay, get the point from the map, and this is how you get the point from the map. You can launch, and then you boot up the RVs to show the map. Then you determine and update the coordinate of the goal location. Okay, so here you can use this. There is a publish point button in your RVs, which is later on David will show you how this thing is executed in the GUI. So the purpose of this process is to, from the map, you get the coordinate, which is the XY location of the particular waypoint you want. So just now I said in the first exercise, after you build the map, you need to identify which point in the real world that you want to give some label. For example, like this point belongs to kitchen, for example. This point belongs to living room, for example. So over there, what you do is like you are going to load the map in AMCL, and then from the map, you can find the coordinate corresponding to the particular waypoint that you determined before. So you're going to write down all the XY point that you want, and you can put in your, there is a file that you can put in for you to run. Okay, right. But that one I will let David to show you. Okay, so then after that you launch the, which is over here, which is the location A in RC Home EDU Learn, and then this one under script there's a navigation.py. Okay, so you want to open up this navigation.py, and then you are going to write in this XY. Then when you run this code, the robot will move from the starting position to the particular waypoint that you want, okay, which is this navigation. So you run, and then, but every time before you want to start this operation, you always need to set the robot current position, which is the starting position. Because without this starting position, AMCL cannot accurately determine where is the starting point. Okay, so this current position or the starting position is very, very important before you start any navigation task. Okay, but once you have the initial point, then the whole system will do the calculation by itself based on the estimation algorithm that I explained before this. Okay, right. So this one by coding. Okay, so I will pass again to David to show you how from the map you can find a waypoint and then how you want to do the navigation by using the GUI and also by using the source code. Okay, right. So David, I'll pass to you. Can you show the demo?
Okay, thank you, Jeffrey. Next, I will show you the demo. First, I will show you to navigate the robot in the gazebo world. We can use the 2D estimate and use the mouse to select the destination point. And then I will show you in the real robot, we will use the code to specify the position of the destination point in the map. Now I will start to first show you the show you the how to navigation in the gazebo world. First, we also need to start our navigation gazebo world. I can use the up arrow to select the recent command here. This is to launch the Jupyter Robot Office world. Okay, and then I will start another tab. So for the navigation, we also can use laser radar, or we can also use a 3D camera on the robot. Now I will show you to use the 3D camera. Okay, Rose launch robot gazebo for 3D camera AM cell demo, and we also need to specify the map file. Map file. Here I can select the folder here. Contacting maps 3. Okay, test 3. We can use the Control plus L to get the path here, copy, and paste here. And we need to specify the name of the map. But pay attention, we need to use this one, not the PGM file. We need to use the YAML file. You can use the rename to Control C. Past. You can Control Shift V or just past. Okay, both okay. All DOM received. That means they work well. And the third is same as Turbo RV's launcher, the view navigation launch. Okay. So this is turn around. Oh. This is a map we have just set up, just built, and this is the real world. The robot just stand in front of this table, and in the RV's world, RV's program, it has some red, green arrow around the robot, all lots of the green arrow, which means the robot estimates the positions where it may be in this environment. And then first we need to use this 2D pose estimate. 2D pose estimate to select which is a click and drag. Click means to select the position of the robot, and the drag means to select the direction of the robot in the environment. After we selection, the robot will move to the position you just select, and the rotate to the direction you just select. And then I will make this smaller and move to the corner of the screen. And then you can use 2D nav go to select the destination point in the map and drag to the direction you want the robot to face and release the button. The robot will find a path here. You can see a line with color with green or red to lead the robot to the destination point. And for example, if we select to the another point, the robot will start to change the path to the new destination immediately. You can find that maybe it looks like the robot has some trouble to get the path to the destination point. It always to turn around and turn around during the time it want to get the destination point. The reason of this problem is the setting of the parameters in the rows. So we can change the setting of the parameter. 陈老师，那个参数怎么说
Parameter.
Parameter, okay. We can use this command here. You can use this one. Rows run RQT reconfig. This will open a dialog to show all the parameters in the environment here. And for example, if we change the destination here, you can see the robot get a new path from here to the destination point, but it still, okay, move a little, hesitate, get the new path on time. So the most important parameter here is move base DW planner and Maxwell theta, which is the max speed of the robot to rotate during the movement. So the number here is 1.0. So we can make it a little smaller. For example, 0.5. Mean y theta also can be a little smaller. This will make the robot rotate not too much. Maybe the reason is different surface of the gazebo world is different with the real world. So the robot, if the robot want to rotate to the direction, maybe it always rotate too much to get the wrong direction. So that we can show you a paper to how to make some change with the parameter here. This is a website, and it's a paper to show you how to change the parameter in the navigation. The robot move to the destination. Okay, it's look like this. So for the gazebo, maybe there is a little problem with the navigation. Few minutes later, a few seconds later. This is the website, a web address of this PDF file. Roads navigation tuning guide. It have the very detailed explain the parameter of all the parameters in the roads navigation, and it will show you how to change the number of these parameters, and where when the number will affect the navigation result. Okay. So this is the demo in the gazebo world, and then I will show you the demo in the real world with the code to select the destination point. 我先把这个停一下，要不太慢了。So this is a real robot here, and you can see the screen. First, we also need to bring up the robot. Bring up the robot. Okay, yeah. And then we also needed to load the map. I have already copied the file. We just get the map in the gazebo world, gazebo environment, and I copied the file to the real robot. So the second type is roads launch Jupyter robot navigation. Let me check. AMCL and map file. You can copy the folder name first, and name of the YAML file first. Okay, all DOM received, and the third one is the Arvis. 这模糊它那个啥了。Okay. Next, we will select the point. Okay. 这里。I don't. Okay. Look like. Okay, how to select the pointer is here. We click here, publish point. We click publish point, and we can see the arrow with the red logo, and we need to pay attention to this part of the screen to show you the position you select. For example, we select the destination point here. Here, we need to remember this number. For example, 帮我记一下1.11 and 3.82. 帮我记下来，负的，记哪了？ The last part is the direction of the robot. Okay. And then we need to find the Python file to specify the position. Here, RC home, education, learn rows. RC home, edu, navigation, and scripts, and navigation. Okay, we need to change the number here. Location A. Okay, save, close. And we need to open another terminal with the command here. Okay. Close, launch, see home, navigation, launch. Okay. I think the robot will move to this position. First, we also need to click the 2D pose estimate button, which we need to tell the robot maybe where is it? Maybe. So here and click the position and drag to show the direction and release the button. The robot will get the path. Get the path to the destination point. Then there is the command. There is the log here to show you the robot now it's going to the point A.看不清楚。Okay, reach the point A and ready to go back. Go back means the robot will go back to the start point. Going back home. Going back home. 没有找到。Going back home. Maybe it needed more time to think about how to going back home. Let me help it. Yeah. Reach home. Okay, maybe some bug here. Because the distance between the sofa and the wall is too small for the robot, maybe it needed to calculate very carefully when the robot passing this this road. Okay, now I will show you the robot how to change the path. I will also select the point here, and I will ask my partner to stand here to obstacle the robot. If the robot selects the path like this, and the robot will change the path to another way to get here. Okay, let's start. Yeah. 对，挡左边，挡下面。So the robot move here, and it found there is an obstacle here. The robot can't go this way, and it change its path to the another way here. 可以了，它不会再看到。读错了。The distance between the table and the sofa is very small. The robot needs to think very carefully. Oh, we can find the log here. A body because valid control could not be found. It moved too close to the table. Okay, turn to another destination. Oh, maybe we need to move to help the robot to leave the situation. 推它，不要搬它。对，推。We can push the robot, not get robot leave the ground. We can push the robot. 它还是从那边走。We also use a 3D camera for this demo of navigation. Of course, we can also use laser radar to navigate in this environment. But according to our opinion, it's much better for the robot to navigate with 3D camera, not laser, because the 3D camera can make focus to the obstacle just in front of the robot. Come on. Okay. That's all, Jeffrey. That's all. Thank you.
Right. Thanks, David, and also all our fellow colleagues in Jupyter Robot. So it's a very nice demonstration. At least, like, I hope all the audience today, appreciate like we actually can do the same thing in simulation and real world, and it work with each other. And you can see really like the robot able to try to navigate in very tight corner, and also the map also like we built in like in a very short time, so we don't really like improve a lot of details. I believe they might have some noise in the map that actually gives some how to say noise during the path planning. But anyway, it's very successful for all the testing, I can say. So I hope like the audience can understand like how we use all these tools for the autonomous navigation for the robots today. Okay, right. So let's come back to my display, and I'm going to show you the arrangement after this. Okay, so we already like finished the content. So I end this this slide with this video, which is actually a TED talk by this previous Google car project manager. Okay, so you can go to the YouTube. I'm not going to play the whole thing, but I just want to show you a few a few scenes. Okay, just to show you like in the middle. Okay, so let me see if let's say you will get. I hope you can see. No, not this one. Okay, yeah, this one. Right. So I just want to let you do some comparison. It's like you can see even for autonomous car, we are doing something very 2D, although they have the 3D radar and so on. But in principle, we still like work on the 2D for the path. For example, like over here, they are like following the path. They do the path planning and so on, which is very similar. And then you can see like they use all this color. So it's very similar like what you see in Jupyter Robot, Tutorbot before this. And then you can see like this is the real view, and this is the 2D view or the sensor view and so on. Then we use the camera, which is the concept of 3D camera, and also the laser scan and so on. So you can see we are actually doing very similar technique. In fact, like for autonomous driving, we actually put a lot from mobile robots into the actual practice in autonomous driving. In fact, like I think like most of the underlayer basics are almost all the same, except like they might need a very high requirement in terms of accuracy, the speed response, and also they need the 3D scan so that you can have a better obstacle recognition, faster recognition, and so on. All right. So I hope like whatever that you learned today will give you some inspiration that okay, it actually relate to like autonomous driving and so on. Like if you would like, this is one of the direction that you can pursue further for your research and also your study. Okay, right. So here we come to the end for today, but before you leave, let me show you the assignment. Okay, right. So for today, you have learned, okay, let's go to the second part of the assignment. Okay, so what you need to do is you combine the speech interaction, which is you learned last week, and whatever that you learned today, which is robot navigation, to develop an interactive robot navigation application. Okay, so you design and develop the robot autonomous navigation application with speech interface using ROS navigation package and gazebo simulator. So you don't need a physical robot, but you just need a gazebo and whatever tools that we just introduced. At least 3 waypoints. So what I want you to do in this assignment is, okay, you can use the same map and same environment in gazebo you do, but what you do is like, just now, David showed you how to get the XY, right, for a particular waypoint. So what you need to do is like in the same environment, you select a few, at least 3, and then you find the XY. Okay, so you say like, okay, this is point A, point B, and point C, for example. Then you try to change the logic of that particular Python code that David put in the location A. Okay, so the algorithm or the logic for the location A is when you specify the location A, the robot will move from point A to, from the starting position to point A. Then from point A, it will move back to the starting position. So that is the logic. You just need to change the logic. So you need to study the code, and then you just make sure that the robot able to go to 3 points. It depends on which point you mention. Okay, so you just want to make it automated. Then you add in with the speech interaction, which is you are going to tell like point A, point B, point C, or you can make it to like kitchen, living room, bedroom, or whatever. So kitchen will lead to your coordinate for point A. Living room will relate to your point B, and bedroom will relate to your point C. And while using your voice, tell the system will recognize that word, transform to the location coordinate that you want, and feed the location to the system and run. So you will have something very similar as just now by just saying, go to kitchen, then the robot will move to point A. Then you say, go to living room, then the robot will from point A go to point B. Then you say, go to bedroom, then from point B to point C. Or you can tell the robot in random, like you can go to bedroom first, then go to kitchen and so on, and make sure that the robot can go to the particular location, whatever from whichever point in the location. So that is the assignment for today. I hope things that you learn for this few weeks, like the speech and also for this one, you should be able to combine, and this assignment is totally possible with the knowledge that you learn in this class, and also some Python programming basic. Okay, so with that, I have finished the content for today. So hopefully you enjoy, and also you make full use of this for your robot development. Okay, so before you leave, we might able to open up for some interaction. If you, let's say you have a question you want to ask, we can discuss a little bit more, like 5 to 10 minutes. If let's say you have a lot of questions after I off the video recording. But before you leave, I would like to make one announcement, which is today we already sent out the registration procedure for Online Challenge 2021. So if let's say you didn't receive the email or you didn't like join us for your kickoff meeting, then maybe you don't receive the email, but all the information are on the website. You can go to our website, you go to like this Online Challenge 2021 page. And then if you scroll down, you will find in the step 1, you will find the online entry form, okay? So talk to your team, you just need to send once per team. So get your team leader or your mentor to sign up this form so that we know you are interested to join this competition and we can send specific information to you for the competition, for the preparation and so on from now onwards. Okay, so make sure this is very important. Make sure you send in this entry application. But with just entry application is not enough for you to qualify for the review. You need to buy end of next month, which is May 24th, send in your technical award challenge materials, which is the video, the paper, and if let's say you have something which is optional, you can send in your team website for the education award. Okay, so by sending these materials and the entry application, then you will be entitled for the review to see if let's say you can enter the final. And of course, once you are selected, then you do the registration and you will entitled for all the awards as well, like the best video, best paper, and so on. Okay, so this is, and the submission site is over here, but currently it's not open yet because it will open somewhere in May. Still early, you still have like 1 month plus time for your development to prepare very nice video and also paper for your robot system. And finally, if you got selected, you need to also complete the RoboCup 2021 registration before June 7th, which is this one is when you're going to the final, then you need to do this registration. But all the selected team, we will send in email for your registration detail. You need a pass key or something in order to do the registration. In fact, now the registration site is not ready yet for RoboCup 2021, but yeah, it will be open. So you need to take care of the deadline. All right. So just now what I say is the 3 steps for you to do the registration, the application, the entry application, and also the registration for Online Challenge 2021. Okay. So I hope like you got all the information. So I will end this session. Thanks, David, and also Max and everyone in Jupiter Robot for the wonderful demonstration. And thank everyone for like attending today. I hope you learned something, and hopefully like if you try and if you have anything you want to share, feel free to talk to us. Okay, so I will stop the recording and we will start our interaction session after this. Okay, thank you.